Hello, welcome to session number 21 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in the previous session I showed you the model and across power performance of that model. I also showed you uh, uh, implementation using a transistorized circuit, right? Implementation using a transistorized circuit and its response also I have shown you, right, across power, and I showed you how to do a large signal tune. Now some points to notice. Okay, so these points to notice are as follows. Okay, so let me just show you, okay, what happens when you take a linear PA and put power through it. So I'm considering the single frequency here, and then on the left side I have class A, on the right side I have class B, right? So in what happens is when I boost the power, right, or when I increase the input power, the gain is flat and then it compresses. So this is what happens in class A. While if you look at the phase is going to expand, right? So the phase expands in class A like this, right? So at the top you see the diagram which is a gain compression, but then you see a phase expansion in class A. In class B, what you are going to see is a gain expansion and the phase just rolls off. So now you can see the difference between the two when it comes to biasing. So if you bias it as a class A, you will get a good gain, but then the phase will pick up like this, right? And if you bias it like a class B, then the gain is going to expand and the phase is going to roll off. Now if you do a two-stage, you can match these characteristics so as to get a better linearity. So this is the point which I wanted to make here. Second thing is, if you remember over here when we took a now the model is flat. The model response across power, the return loss response is flat, right? While in case of the real circuit, you see that the impedance varies with power, and that is also shown here on the Smith chart, that impedance varies with power in the real circuit. So this is just a cartoon representation. Let's see in the real circuit what it is, right? So in a real circuit we have seen, sorry, we have seen this, the same thing as I was mentioning. Okay, it is the same thing. So this is across frequency across power, and this is across frequency output across power. So now you can see that there is a change, right, of impedance with power. So if you represent this in terms of across power, you can see here that this is what is happening to the impedance, and that's what I have done here. So this is what is you are going to see practically. So practically in the circuit, you are seeing the same thing, right? And similarly on Smith chart, you are seeing the same thing as I have drawn in this picture here, right? Maybe it may be on a different side, right? So it may be on a different side like this maybe. Okay, so it may be on a different side like this, but the idea is of a large signal tune is to get it matched under compression. So this is a single tone, right? Now this is practically it is the same thing, right? You see here, right? This is what is happening for a given frequency, right? Across power, and this is what is happening from the circuit, right? So now this you have to keep in mind, and you can use this to improve the compression characteristics as we have done in large signal tube. Another thing is that across power you're going to see something like this. Now this is kind of rotated, so it really doesn't matter, you can rotate it back. Okay, so you can basically rotate it back the way they are. So the way they are like this. So I'm not going to change it, but you got the point, right? The point is, the point is, hang on a second. Okay, the point is that you have to match at the compression, and the small signal can be mismatched. And we have also looked at the K, last signal K, and the last signal K, you can see here, the large signal K is doing something similar, isn't it? This is large signal K, and what you see in this diagram, I have drawn large signal K, right? So large signal K is going to do this, right? And then I have also talked about the gain droop, right? So there is going to be a gain droop like this, right? So all these are not captured in the model, which you see in the real circuits, right? So you see in this real circuit. Now what I'm going to do now next is I want to look at the two-tone characteristics, and I've already shown you in the previous session what are the limitations of a two-tone characteristics. So I'm going to set up this for two-tone analysis. So let's go ahead and do that. So I'm going to go to ADS, and I'm going to just make a copy of this. So I'm going to call this as copy cell and call this as two-tone characteristics. Okay, so I'm going to make it a two-tone characteristics. So where did it copy? One more time, let's see. It copied to Balin folder. Mistake. Okay, so I will move it to here. Move. Okay, so now I can go ahead and modify this for two-tone analysis. So first of all, I'm going to switch off the sweep. I don't want to sweep it. Okay, and I'm looking at only one power level, which is going to be maybe 10 in, right? 10 in. Okay, so okay, so now I have to set up some more things. Like for example, I have this RF frequency, right? So I will put another thing which is called offset. Okay, and offset frequency is, let's say, 1 megahertz, right? So that will be 0.0001 gigahertz, right? So I will add that. Then I will say RF frequency 2 will be equal to RF frequency plus offset, right? Add. So this now is two tones, right? And then the power is 10, so I'll put power 3 dB down power in both of them, right, in two tones. So what I'll do is I will go here, and instead of P1 tone, I can make it a PN tone, right? So all you have to change is the name. So once this is done, so my power, my frequency 1 is this. Now my frequency 2 is going to be this, right? And then power 1 is this minus 3 dB, right? And then I can say add power 2 is 3, the same minus 3 dB, and I'm done. So I have got two frequencies. Again, I have to put the units here. Okay, so two frequencies, two tones, which are 1 megahertz apart, and then I'm putting half power in each tone, and then I'm putting it through a circulator into the same PA, and I'm getting the output. Now here I am not going to do anything. I'll just cancel this out, or rather deactivate this, and I would hit simulation here, right? So I'm going to hit simulate. Okay, one more thing, you have to add one more frequency here. So RF frequency 2 you have to add, right? Add. Fine. So say okay, and then you hit simulate. Okay, now what I'm going to show is, first of all, I'll show you the mix component. Okay, I should show you both the mix components. So I'll just put mix here. Okay, so now you see that there is what RF frequency and RF frequency 2, right? Okay, so if you see 1 and 0, okay, so one tone is this one. So let me just change the preferences in grid, and 0625 and 1, and say okay. Okay, so one frequency is, one tone is this one, right? And another tone is this one, correct? And these are represented by 1 0 and 0 1. And then I am going to look at this plus this, so 1 plus 1, so this is going to be twice of f2 minus f1, right? So twice of f2 minus f1 would be this one. Okay, so this one is twice of f2 minus f1. and then twice of F2 minus F1. And then this one is going to be twice of F1 minus F2. So you can see, read from here, mixed component is 2. Twice of F1 minus F2. And this is twice of F2 minus F1. So these are the three components. Two of them are the linear components at the output. And then there is intermod IP3 components here. And their indexes are, so you know their indexes, right? So I can put their index as 0, right? And then let me write 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? And let me just change the font. Okay, can't change the font. Why can't I change the font size? Properties. Okay, let's put it here. So we have 0, maybe a bigger font size. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So now you know which component is what. So the two tones are index 5 and 6. No, 4 and 5. 4 and 5 are the two tones, and 3 and 6 are the intermod products. So you have established this, right? So what you have established, the two tones are 4 and 5, and so basically you have established these. So I can get rid of the table, not required. Okay. So these are my indexes which are of interest. Okay, so these are my indexes of interest. 3, 6 are the intermod products, 4 and 5 are the tone. Okay, so now I am going to write the equations. So let's go here. Let's enable this. So I will say P out 1 is going to be V out of 4, right? V out of 4, or rather, yeah, so let P out be there, doesn't matter. I'll add P out 1. Okay, so this is the total output power, and P out 1 is going to be index 4 and I out index 4, correct? Add. Then P out 2 is index 5 and I out index 5, correct? And then I am 3 lower, right? I am 3 lower is going to be index 3, right? And I am 3 upper is going to be index 6, correct? And then I can convert all of them to dBm if I want to, right? Or I can add the total power, right? So in this case, I can say P out dBm. So P out dBm I'll say as P out 1 plus P out 2, isn't it? P out 1 plus P out 2 is the total power in P out dBm, or rather say add. Okay, so the power in two tones is, this is the total power, right? This is the power in two tones in dBm is P out 1 plus P out 2, right? And then the power in IM components, right? Okay, so power in IM components, I will call this as IM in dBm is going to be equal to P out IM3 lower IM3 lower plus IM3 upper plus IM3 upper, correct? So that is the IM, and the gain is going to be equal to the gain for the tone, right? So this will be P out dBm 1. Okay, so 1 minus RF power, right? And then so that's that. What else is there? Reflection. Okay, so in the case of reflection also, what will be the reflected power? It will be in the two tones, right? No, but the two tones are not on the input side. Input side is just the fundamental, right? So let's see what happened to the fundamental here, right? So the fundamental, huh? So let me just click OK here for now. Let's put back the mix component. Equation, mix table, mix table. Okay, so I'm putting two tones, right? So my reflection coefficient would be because of 4 and 5. That's correct. So reflection would be 4 and 5. So reflection would also be 4 and 5. So this reflection would be this one. So this one will be 4, right? And I'll just add this, right? Plus 5. That's the total reflected power in 4 and 5. Right, and then in dBm it is this, and then this is return loss. Say okay. So this is what the return loss is going to be. So once we are done with these, I am going to click simulate. So is there a warning? No warning. So let's look at what happened to the gain. Okay, so this is single frequency point, so really doesn't matter. So let's do the sweep here, enable the sweep. So this is called RF PWR. Okay, so this is done and hit simulate. So this is what is happening to the gain. It was 19.9 to start with, right? And then it is going to compress, correct? And then the output power of the two tones is going to be this, correct? And then I am going to look at the IM3 power in dBm is going to be this, correct? So really I should see the slope starting at this point, right? I'm not concerned about here, I'm concerned more about here, right? So now let's put this on the right axis. The gain is on the right axis, okay? And so the compression has really started beyond 0. Okay, so now I am supposed to determine TOI and SOI. So for SOI, I haven't put here any component, right? I have put TOI components. I have to put SOI components also. So for that, you go back to your simulation and or your mix table. So I have to do this again. Okay, so let's look at the mix table again. Mix table. Okay, so I am interested in F1 minus F2 and F1 plus F2, which are these, right? So this is up to here 8, then 9. So basically 9 is F1 plus F2. So 9 is F1 plus F2. Correct? And then F1 minus F2 is 1 megahertz. That is 1. Correct? So I have to write equation for 1 and 9 also for SOI, right? Okay. So I will go here, and so I will call this as IP2, right? Just one second. Okay, so I am going to add here for IP2 or IM2. So one IM2 component is 9. That is F1 plus F2. So this is going to be upper, not lower. So the lower one is going to be 1. F1 minus F2. And IM2 upper is going to be index 9. Index 9. Correct? And say OK. So now we are done with this, right? So now I have got the total power in IM2. So that also I have to add here. Okay, so this is the total power in IM2, right? So the total power in IM2 is going to be IM2 lower and IM2 upper. Add. Okay, so we are done. So I'm going to simulate again. So here I am going to do the sweep. So I'm done with this. I'm going to put back the RF power sweep, right? Okay, so once this is done, I sweep that and I have this. So now I have IM2 in dBm also. Okay, so its slope is going to be smaller than the IM3 slope. Okay, and I have to find out the intersection of these, right? So I have to find out the intersection of this to establish the TOI and SOI. So that's what I'm going to do next. Okay, so linear gain. So all I have to do is write the line of equation for lines, right? So if I do new and marker new, so 2 and 3 marker are going to give me equation for a line for the the linear gain. And then marker new, I'll put this over here, somewhere over here where the compression starts. Okay, 3 and 4 sorry, yeah, 4 and 5 is going to give me equation for TOI, and 6 and 7, marker 6 and 7, so I'm going to put them here. Come on, 6, and I'll put one more marker, 7 is going to give me equation for SOI, 6 and 7. Correct? So this is there. Another thing is I want to look at the spectrum. Okay, so the spectrum would be P out dB. So first of all, I want to plot the spectrum wherever this marker is. So what I'll do is I'll find the index of that marker. So I will say n is equal to find index, find underscore index, and you have to find out index in what? You have to find out index in independent of M1, and that is basically RF power, right? That should give you the index. Okay, so this is written the other way around. So RF power comma, and okay, so now if I a table here for n. Table for n. Okay, so the n is the index. So n is, sorry, so n is the index of m1, correct? So this is a mixed component table. So this is the mixed components, and n is the index of m1, correct? And at that point I want to plot the spectrum. So I will go here and put out P out in dBm, and I will look at the trace expression. I want to get the variable info and P out dBm. So you have power as the first index and second index is the frequency. So I'm looking at the nth value in power at all the frequencies, right? So the way to write is I am looking at nth value of power for all the frequency components, mixed components. That's it. And here I would just change the plot type. Trace type is bar, like this. Say okay. Okay, so now your IM components are here, so I'm going to zoom into that. Okay, so if I put a marker here, so this is the power in the tone, okay, for this given input. So the input power is minus 26, the output power is minus 9.3. So what's the gain here? 26, 16, 16.9, that is 16.9 roughly is the gain, and then plus 3 dB, right? So 19.9 is the gain. And then the IM product is over here, right? And I have to do the difference of that. So select this two and say delta mode on. What happened? Okay, so the reference is this one. So okay, so this is dependent value is 100 dBc, right? Minus 100 dBc. So the independent value has to be the marker name delta reference. Reference has to be 8. Okay, so we have to change this. Okay, so 9 referenced with 8. So 9 reference with 9 will not work. Okay, so I have to turn this off again. Delta mode off. Okay, so delta mode shift delta mode on. Reference is 9 or reference is 8. No, reference is 8. So minus 100 dBc, correct? So you are reading minus 100 dBc as the, yeah, minus 100 dBc is the IM3 component. Now if you move this, okay, so if you move marker 1 and you go towards compression, okay, so these values are going to go up, right? And you see here that the IM components are coming up. Okay, so as this compresses, the IM components are going to go up. So now one more thing I want to do is on y-axis I will do auto scale, right? And so you see here the IM components are going up. So let's look at 1 dB compression, which is going to be 18.9. Okay, so these components are coming up. So look at 1 dB compression, which is 18.9. So at 18.9 you are seeing minus 28 dBc. Okay, so now you can see what compression does to the IM components. They grow much faster than the linear component. So that's all I wanted to show you. They grow much faster than the linear component once the compression starts, right? So now I am going to put you on a hold, and I am going to write the equations for SOI and TOI. Okay, so let's keep this aside. So I'm going to write the equation using these M3, M2, M4, M5. I want to find the intersection of these lines. Okay, and that will be TOI and SOI. So I'm going to put you on a pause. Meanwhile, I write the equation for TOI and SOI. Right? Okay. Okay, so I have written the equations for TOI and SOI based on the slopes, and TOI turns out to be 41.5 and SOI turns out to be 54.6, and this basically is more or less close to what we have placed here, 41 and 55. So that's what you're going to see here, right? So that's the two-tone analysis, right? So in two-tone analysis, what did we do? We are looking at IM3 components in terms of dBc, and we can see the effect of compression as these ion components are going to grow, right? You can see they are growing much faster than once the compression sets in. The ion components grow much faster than the linear gain components, and at TOI they are going to be equal, right? So TOI is 41 roughly and SOI is 55, right? So this completes this small exercise on two-tone analysis of a PA. Now same thing can be applied to the practical circuit also. There's not much difference here, right? You can do the same thing with the practical circuit. So after this two-tone analysis, in the next session, I'm going to present to you modulated signal. And I'll start with QPSK signal, DQPSK, and then QAM signals. Right, so those I'm going to create from ADS and then put into a PA. Okay, great. Thanks a lot. Thanks.